So it's important to know that solutes can change the properties of water. So colligative properties, for instance, boiling point, melting point, and osmolarity. Think about adding salt to water. So if you have, if you're making spaghetti or something like that, you're going to be boiling water. I suppose you can boil water for any number of other purposes. But you're probably going to want to add salt to it. And what you're going to be doing is you're going to be disrupting the melting point or the boiling point. You're changing that hydrogen bond network that exists between all of those different water molecules. So non-colligative properties, viscosity, surface tension, taste, and color can also be disrupted. The cytoplasm of cells are highly concentrated solutions and have high osmotic pressure due to dissolved solutes. So the cytoplasm is not, we already talked about it being a viscous solution, and it's certainly water-based, but it's not just water. There's a bunch of other dissolved salts in there. Okay, so the ionization of water is maybe one of the more important things. I know that I use the phrase more important or most important. I use those sorts of terms and that terminology over and over again. I apologize. Ionization of water is one very important part for biological systems because you talk about them as a buffered system. So OH bonds are polar and can dissociate heterolytically, so that H2O can break up into a hydrogen ion and a hydroxide ion. So a proton and a hydroxide ion. And I will do my best to use the terminology of proton. I will try to use proton as much as possible when describing H+. So we see that dissociation, and that's a very rapid and reversible process. Most water molecules remain unionized or unionized. Thus pure water has a very low electrical conductivity. So that's one thing that I know that you talk about in Gen Chem 1, or at least I talk about that in Gen Chem 1. If you have pure water, it's not going to conduct electricity very well. Throw some salt in there, then it's a little bit of a different story. The equilibrium is strongly to the left, low KEQ. The extent of the dissociation depends on the temperature. Okay, now proton hydration. Protons do not exist free in solution. They are immediately hydrated to form hydronium ions. So that's a very important thing. I know that I struggled with that in organic chemistry, I think. Yeah, probably Chem 2 as well. Anytime that this came up, really, because I just imagine that there are hydrogen ions floating all over the place. It's not really an accurate representation because they are part of a hydronium ion. But what does a hydronium ion do? Well, hydronium ion can very easily give up a hydrogen ion or a proton. Okay, so KEQ is equal to our products over our reactants. So H plus, concentration of H plus times concentration of hydroxide divided by the concentration of water. A hydronium ion is a water molecule where the proton associated with one of the non-bonding electron pairs. So when we talk about this, we've got, there we go, there. And then we've got this third one for that hydrogen ion to make our hydronium ion. Hydronium ions are solvated by nearby water molecules. The covalent and hydrogen bonds are interchangeable. This allows an extremely mobile movement of protons. So this is also known as proton hopping. We see this proton hopping right here. We've got our hydronium ion right there, and that hydronium ion is going to give up a hydrogen. It's going to give up that proton to this water molecule. Well, this water molecule, now it's a hydronium ion, that's going to give up a proton. So it's almost like to get from point A to point B, well, you don't have to get through that. Instead, you just use this cascade of these different molecules, and these different water molecules convert them to hydronium ions. That's how you get a proton to this water molecule down here. You don't take this proton and move it. Instead, you just make everything along the way move that proton along. Okay, so the ionization of water, concentrations of participating species in an equilibrium process are not independent but are related via the equilibrium constant. H2O yields a proton plus hydroxide ion. KEQ can be determined experimentally if, it is 1.8 times 10 to the negative 16th at 25 degrees Celsius. The concentration of water can be determined from water density, which is 55.5 molar. So our ionic product of water, our K sub W, is equal to KEQ times the concentration of water, which is equal to the concentration of hydrogen protons times the concentration of hydroxide ions, which is equal to 1 times 10 to the negative 14th molar squared. In pure water, our proton concentration is equal to our hydroxide concentration, which is equal to 10 to the negative 7th molar. Okay, now that's all very important because it leads us to a discussion of pH. So our pH is equal to negative log times our proton concentration. pH is defined as the negative logarithm of the hydrogen ion concentration. So what we will see, it makes this all very simple, that kind of derivation that we just did. Now what we have are basically two equations. Well, negative log times the hydrogen ion concentration minus log of hydroxide ion concentration is equal to 14. pH plus pOH is equal to 14. Okay, so if your pH is 7, what's the pOH? It's 7. If the pH is 6, what's the pOH? 8. Okay, so pH can be negative if our hydrogen ion concentration or our proton concentration is 7, but in a neutral solution, our pH is going to be, if our proton concentration is equal to 6 molar. Now in a neutral solution, our proton concentration, our hydroxide ion concentration, the pH is 7 ultimately. All right, so this is really the foundation for a discussion of amino acids and how they ionize. But just remembering this and understanding pH and pOH and everything like that, it's going to help you out quite a bit.